Three laws over the next 2 weeks. There's a couple of equations, there's a couple of diagrams, and there's some definitions that we've got to master. Now, before we start on Newton's first law, we've got to look at mass. Mass and weight are different things, and this is something that's crept into the English language, that they're used interchangeably. Like, oh, I weigh 60 kilograms, or I've put on weight, okay? We'll learn in future lessons why that first statement is not really correct. Now, the dictionary definition will make more sense when we get to Newton's second law, but the better definition is it's how much stuff an object has, or how much inertia. So, okay, we can often call mass the inertial property of matter, but we've got to then go, well, what does inertia mean? So today's lesson is going to be on inertia. Inertia is how much resistance an object has to change. So if I get a 1 kilogram object and I shot put it, right, it's going to accelerate because I apply a force. If I then take something that has twice the inertia, twice the resistance to change, it has twice the stuff, and I try to shot put it, it's not going to accelerate by as much because it has more resistance. Okay? It has more inertia. So I could replace the word mass with inertia. So if somebody is 60 kilograms, can you stop that? If someone is 60 kilograms, they have double the inertia of someone that is 30 kilograms. Okay, they've got more mass, they would be harder to push around. And that should make sense. Little year 6 kid, you give him a shove, he goes flying. You go up to a first rugby player in year 12, give him a shove, he won't budge. Okay? It has to do with how much mass that they have. So, we know about mass, we've already kind of looked at it. It's a scalar quantity, it's just a magnitude, and we measure it in kilograms. And we looked at why it's the kilogram and not the gram, because of the French Revolution. Now, we're going to quickly talk about this guy. He was centuries ahead of his time. So back in the 1600s, very different time in England. You had the Black Plague, you had oil lamps, they were killing whales and getting the oil out and burning it, coal. This was before the Industrial Revolution, okay? He was a weirdo. I'll just quickly go on a bit of a 5-minute story time about Isaac Newton. He was strange. Now, it's kind of like, we're all familiar with Sheldon Cooper from The Big Bang Theory. Yes. Now, he was kind of a Sheldon Cooper. He was a little bit strange. He didn't really work very well socially, but incredibly intelligent. It was thought that he may have had Asperger's autism, which is known as a high-functioning autism, where you're incredibly intelligent mathematically and spatially and with numbers, but you're not really good with the social side. Okay, so he was a little bit rude. He didn't really, and here's the next thing. He was born into a very wealthy, noble family. Okay, so he would have his gloves and his cane and his top hat. He come from a well-to-do family. And he didn't like talking to people. He thought that they were all below him. He was a little bit superior, kind of like your Sheldon Cooper. Now, the other idea was that they think that he was suffering from heavy metal poisoning, from mercury poisoning. Because he was a wealthy man, back then you had your class societies. You had your aristocrats, you had your workers, you had your povos, you had that kind of, you probably learned that in, I don't know, humanities or something. So, what you did is you showed off to everyone else how wealthy and noble you were by the clothes that you wear, by these lapels that you have on your jackets that you attach your epaulets, all of your badges. You have your silk ties, you have your fine silk gloves and your top hat, right? And if you couldn't afford, because back then laundry was a very, pretty wealthy thing to have, okay? So back then a lot of people are smelly and dirty and their clothes are dirty and they're in tatters, unless you're wealthy, and then you can get, nice clean clothes, okay? And in fact, back then they didn't have dyes, they didn't have, most of the coats were just normal crappy browny beige colours. They didn't have reds and purples and blah, blah, blah. You could get fine silk from the Far East, oh wow, you know, that's expensive. So you walk around with this fine, bright red silk tie. You go, look at that guy, he's got a lot of money. Anyway, your noble gentleman had top hats, and you would, how do you do, and you'd walk around with your top hat. And if you had a slouch hat, you go, look at that povo, his hat's all slouched over, what a povo. So what they used to do is they'd keep a stiff-brimmed top hat. I mean, this is weird, yeah? We are weird creatures. We are very social, weird animals. What they used to do is they would rub mercuric salts. So that's just a certain type of salt that had mercury in it, and that would get into the hat, and it would make the fabric nice and stiff. Okay? And so you could have a stiff brim hat, and it would keep its shape, your top hat. Now, who here is familiar with the Mad Hatter from Alice's Adventures in Wonderland? Yes? Is it Lewis Carroll wrote that? The Mad Hatter. Now, if you've read the book, who's read the book? Hey, let's see. Let's test you now. When Alice is walking around through the woods, she comes across the Mad Hatter having a tea party. Right? Who is he having the tea party with?
A rabbit.
Rabbits, woodland creatures. Aaron? He was with himself. Disney, or Walt, I don't know, Disney, Warner Brothers, when they made the cartoon, they thought, well, let's pitch it at little kids. Let's make it all funny little fuzzy bunny rabbit and another bunny rabbit and a fox, right? In the original book, in the 1700s, he was sitting by himself. Now imagine, you're a little girl walking through the woods and there's this man having a tea party with himself. You would back the hell away, right? But no, she goes down and she has a tea party and she starts popping pills and weird stuff happens. Yeah? So, the Mad Hatter was an actual type of person in England in the 1700s. They were suffering from heavy metal poisoning. What was happening was the mercury would seep in through the fabric into their skin and it got into their body. Now, us humans have evolved to deal with our environment. We take in metals and we excrete them. We take in sodium, magnesium, potassium, zinc, iron, calcium. These are all good things. Yum, milk, yes. Leafy green vegetables, yes. Blood, wonderful. If we have too much sodium, we pee it out. All right, our body can excrete it because we've evolved an excretory system to remove excess minerals. Mercury had been locked in rocks. We did not evolve with mercury. We did not evolve with lead. Then come to the 1700s, you find this rock, you crush it up, you throw it into a furnace, you add a little bit of carbon and out trickles this gold and silver metal. It's called mercury. And you can do the same with lead. Lead has a very low melting point, so you can extract it quite easily, right? So now you've got metal on its own. Our body doesn't know what to do with it, all right? It doesn't recognize it. So when it gets into our body, it stays in our body. It accumulates in our hair, in our bones, and in our brain, okay? And so if you suffer heavy metal poisoning, it accumulates in your brain and it affects the chemistry or the biochemistry of your brain. You go a little bit loony, okay? So the Mad Hatter was, again, these rich, powerful, noble, aristocratic gentlemen that were all going a little bit crazy, okay? And so they were giggling maniacally and having tea parties with themselves and doing stupid things. Now, this bloke, he was buried, I want to say Oxford or Cambridge, one of the English universities. His body was buried there back in that year. They exhumed his body a couple of centuries later in the 1900s and they took trace samples of his hair and yes, they found excessively high amounts of mercury. So the idea was that he was suffering from mercury poisoning. Another one, lead. Now we know lead's bad. It used to be in, how long has my story time been going for? Lead is bad. But they found that if you added lead to petrol, it would stop engines from knocking. It would actually, when it was entering into the piston, it made the engine run a lot better, more efficient, less damage. And this bloke discovered that, put lead into petrol, and then you can literally trace when it started, and you can detect all of the lead in the atmosphere. And it's just on a graph, it goes whoop, and that was the year that they introduced lead in petrol. Took them about a decade or two before they went, oh crap, hang on, it's now in the atmosphere, it's in the plants, it's in the fish, it's in our bones. The lead that was put in the petrol is trapped in the bodies of all the people that are still around. And then they had to bring in unleaded. So it was a lead substitute. So unleaded petrol, your engines, you had to put in unleaded petrol. Lead, when it was first extracted, I want to say about 400 years ago, you throw it into a fire, you add a little bit of carbon, out trickles lead. It was really useful. It was easy to extract. You just had to find a black rock, shiny rock. It's called galena. It's a mineral. You dig it out of the ground. There's lots of lead atoms in there, but it's ionic, all right? Can't hurt you. Lick it, nothing's going to happen. If you get pure lead, that's when the metal starts to do its bad stuff. Have you heard? Oh, what's the symbol for lead?
PB.
What's the Latin word for lead? Plumbum. Plumbum. Does that sound like a word we have in the English language? No, really, it should.
Sounds like plum.
Plumbing.
Yeah.
Plumbing. The word plumbing originated in Italy in Roman times, where they discovered that this metal, this lead, it was malleable, it was ductile, it was easy to make. You could turn it into a pipe. You could put water through that pipe. Then you could bring the pipe into your house and turn a little tap, and out will come the water. That's great. You don't have to go to the well. You can have water in your house. So the Italians were very, very good at having these aqueducts and then water running into your house. But only if you were rich and noble. Yeah. Povo people still would have to take their bucket to the well. So you've got rich and powerful people. All the lead in the water. The lead's now in you. The idea again was Nero, who was the Roman dude in charge of the army. Roman general. He apparently made some bad decisions and led to Rome burning. Right? So again, the idea was that he was suffering from heavy metal poisoning, and he's in charge of the Roman army, and when they're warring with all the other countries, of which I don't know, he's saying, let's go and send all of our troops over there and fire our stupid mistakes, stupid commands. That led to the downfall of Rome. When I was your age, I had a computer that had a CD-ROM drive that could burn CDs, right? So you get a disc, and it could hold 700 megabytes, right? And so if you made it an MP3, it could hold 80 minutes of music. 80 minutes on a disc, right? And so you put it in, and you drag in your songs, and you click burn, and you'd wait about 90 minutes, and you come back, ding, your disc's ready, and you can put it in your compact Discman, and you can walk around and listen to music. The software program that I used was Nero Burning Suite. It was the software program that was used to burn, and the little icon was the Colosseum with flames. Right? It's Nero burning Rome. Anyway, plum. Have you ever run towards a cricket pitch and bowled a cricket ball and said that was plum? What does that mean?
Like, dead center.
Dead centre, straight at the middle stump. That was plumb. Again, that word plumb has its origins from the Latin plumbum. When people used to build buildings, if they wanted to make sure that the wall was level, they would hang a lead bob on a string. They would put the string at the top of the wall, and if the plumb line lined up with the wall, then it was plumb, meaning it was dead level.
They did that with Mercury too, right? They put Mercury in the spirit level thing.
Possibly. But Mercury is Hg, which is hydroargentium, which is Latin for quicksilver. Whereas plumbum, that's plum. So they had a plumb bob or a plumb line. Geez, I just wasted a lot of time. Let's get back to this. Oh, okay, this guy. So they reckon a couple of things. Wealthy, very bright, a little bit Asperger's, a little bit mercury poisoning, but his mind worked, right? He could explain the motion of the planets. He could explain the motion of objects here. He could explain the motion of us around the sun. And he realized that we're all governed by the same 3 rules, okay? But he couldn't explain them in the mathematics at the time, because the mathematics was only 400 years ago. It was very basic. So he invented his own branch of mathematics, and he called it calculus. And it's being taught right now to the year 12s, and they're all pulling their hair out because they've got to learn calculus. Now, that's how smart he was. He said, well, I want to explain it, but the current maths doesn't explain it, so I'm just going to invent my own mathematics to explain the motion and blah, blah, blah. There's some other cool stories. Shall I keep going?
Yes.
I'm in no rush. You've heard of Grey's Anatomy?
Yeah.
Yes. What's Grey's Anatomy?
Show.
It's not a show. Try again.
It's life.
Anyone want to try again? It's not a TV show.
TV series.
It's not.
Based on a true.
Is it an anatomy?
And
The anatomy of Grey, maybe?
It's a documentary. So it's a book.
Ah, it's a book. It's a book.
Yeah. It's not a TV show.
it should be.
I don't know, House MD, I think the opening of House or the opening of Grey's Anatomy. Now, there's some crazy stories about Isaac Newton. He was a very curious mind. He wanted to know how stuff worked, as many people do. There were stories of him staring at the sun for as long as you could, as long as he could possibly bear. He just wanted to know what the sun was about. He looked at it through a telescope, staring at the sun to see what it was doing. And he's got these very bad, scars at the back of his retina, and he was confined to his living quarters for 4 days with splitting headaches because he stared at the sun for too long. What have we learned about staring at the sun? Don't do it. Now, there's other stories where he was, he lived at the university. Back in the day, you had professors, and the professors lived at the university because it was very important that a country have very intelligent men, because then they could build bigger bombs and cannons and weapons, and you want to have your intelligent men. Nowadays, professors go there and teach kids. Back then, professors would live at the university and just figure stuff out. There are stories of him waking up and putting his shoes on, and he's sitting and he just started thinking about mathematics, and he would be stuck paralyzed, just in thought, thinking about an equation. Do you want to open that for me, Rocket? And he would just not turn up. People would go, Where's Professor Newton? And he's just sitting there on the side of his bed, just locked in thought. There's another story where he took a leather strapping needle. Now, a strapping needle is a very large, thick needle that they would use to literally sew leather together, right? For saddles, yes. So, huge needle. Now, the story is he took this strapping needle and he placed it between his eye socket and eyeball and rolled it backwards and forwards to try and figure out what was behind his eye. He didn't really find much, right? Because back then, they didn't have Google, they didn't have medical books, they didn't yet have Grey's Anatomy. They didn't know how the body worked. Scientists used to go to graves. Scientists used to go to graves in the middle of the night and dig up bodies and drag the bodies back to their labs and hack them open just to see, what are we made of? Oh, look, there's a vein there and some muscles there and a ligament there. That's why you have the midnight shift is called the graveyard shift, because you have to have people actually at the graveyard to stop all of these crazy scientists stealing bodies. Okay, and also they thought that occasionally some people would fall unconscious and they think they're dead. They bury them, and it turns out that they were still alive. And there's reports of digging up coffins, and there's scratch marks on the coffin, and all of the nails of the dead body were ripped off because you wake up and you're in this coffin. Right? For a while in the 1700s, they would tie a little string to the foot of the dead body and have a rope. The string would go up a tube through the earth to the surface, and there'd be a little bell. And so the graveyard shift, the bloke would be there overnight just listening for bells, because occasionally, I don't know how many lives it's saved, but someone would wake up because they're just, unconscious for a couple of days. And then they would start kicking around. Ding, 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 ding. The bell would start ringing. You quick dig him up, he's not dead. Now, cut forward to, I don't know when this was. This was another scientist called Mr. Gray, Dr. Gray, probably Professor Gray. He cut open the body and he saw all of these wonderful tendons and muscles and ligaments. He employed a very good artist to take these images, and he named a lot of all of the muscles and ligaments and, carotid artery and on myotius and clavicle and all of these things here and mandible and all of the, you know, he's sitting there with his dead body, slicing back the skin, slicing back the fat. Oh, look, here's a ligament. Draw that, Enrique, or Pierre, or whoever it was. I think it was a French. It was a French artist that he employed. Okay. Now, Einstein didn't have this. Newton didn't have this book. No, you're not. Newton didn't have this book, right? So he was trying. Had he had this book, he could have gone to the head section of the book and looked at the eye. He would have seen that there were some ligaments at the top of the eye, ligaments at the bottom, and that makes your eyeball go up and down. And then there's a couple of ligaments on either side, and that's what makes your eyeball swivel left and right. He didn't know about that. And then there's an optic nerve that goes into the brain at the back of your eye socket. There's, you know, straight into the brain.
Did he go blind after that?
No, he didn't really find much. Okay? So all of these... Now, the reason why this book became so important and so useful that it remained the textbook that med students had to purchase, because they had to learn all of these ligaments and muscles and veins and arteries and all the organs. They all have these Latin names. And it still remained Latin to help, you know, Chinese doctors, Spanish doctors, French doctors, English doctors. Everything's called the same thing. It's all Latin, right? It's got its origins in Latin. These med students would have to buy Gray's Anatomy. And so when Dr. Gray, season 1, Dr. Gray is not a doctor, she's a med student. And so the show was named after the medical book that she needed to have and read and use. So, he was weird, a little bit quirky, very smart, and he was possibly, I mean, I reckon about 100 years before his time, had he not been around, it'd be a fair statement to say that our technology would be 100 years behind. All right, so think now, we would have the current technology of the 1910s, the 1920s. It's a big statement, but he did this, and then all of the scientists, he published this famous paper called Principia Mathematica. It was in Latin because in the 1600s, English people spoke Latin. They didn't speak English. It's all in Latin. And again, they were published, they were sent across to all parts of the globe, and all of the scientists read this book and went, holy crap, he's right, everything works. Let's take his knowledge and start to advance on it. And that's when you started getting engineers, people, and then the Industrial Revolution, and then whoop, this is where we are today with iPads and fidget spinners.
Yeah.
Okay? All right, so let's get on to his first law. Now, this law, I would encourage you to highlight it. If you have a highlighter, I would like you to be able to regurgitate and spit out all of the 3 laws in their words that they are. So, try that again, highlighter mode. An object at rest will stay at rest, and an object at motion will stay in straight line motion unless we apply an unbalanced force. There's a lot of stuff going on in that statement. Okay? So the first one, we could almost say that that's stationary inertia. And then we've also got straight line motion is kind of moving inertia. If I've spelled it correctly. Inertia. Inertia. Intertia. I have spelled it wrong. So inertia can be at rest. So all of the objects on the table right now, they are at rest. And they want to stay at rest. If I want to move something, I've got to apply an unbalanced force. Right now, the forces are balanced. But if I give it a smack, then it's an unbalanced force, and its motion will change. Okay? But also you can have objects that are already moving, and they want to stay moving. And they'll move in a straight line unless, and that's why I've capitalized it, unless there's an unbalanced force. It has to be unbalanced. Because as we will learn, gravity's pushing the box to the table, that's at rest. The forces must be balanced. So there's actually two forces acting on this object. You've got the gravity weight force acting down, pushing it down. The table's pushing up. Equal and opposite, but we'll learn about that later on. Okay, me, at the moment, I'm stationary. There's two forces acting. Weight down, floor's pushing up. If I want to accelerate, then I need to have an unbalanced force that accelerates me. Okay, so let's just quickly look at this diagram. I've got a few fun videos we'll watch before we finish, but I have to stop the screen recording or we'll get copyright violations. So let's just think about a bowling ball that's rolling along a bowling alley, okay? And for now, ignore, there's no spin. It's traveling in a straight line, okay? Ignore friction. Bowling alleys are very, very ridiculously polished. They're very low friction, and you might know that if you've tried to walk down a bowling alley, you fall over. They are slippery. They're designed to be slippery because the bowling ball does not want friction. So just ignore friction for now. That bowling ball will continue traveling in a straight line motion unless an unbalanced force acts. Now, someone give me the fate of this bowling ball. What could happen if you throw a bowling ball down a bowling alley? It hits the pins. All right, let's look at that one. So the first one, here's my wonderfully copied bowling ball. All right, and then we're going to make it like, look at roll. All right, it hits the pins. In which case, it would stop. So we'll just write here, for now, a very simple model here, we'll just say hits the pins and it stops. Okay, so we had a force must have acted, an unbalanced force act on that ball and it changed its motion. But at the same time, we had a pin was just sitting there minding its own business. It had stationary inertia and it goes flying off. Okay? So it accelerates. Okay? So there's two ways to look at it. We could say that the moving inertia, it had a tendency to keep travelling in a straight line until the pins exerted a force on the ball, caused its motion to change. That was one example of inertia. The next example could be the pin was sitting here at rest and it wanted to stay at rest. It had a resistance to change, it didn't want to change until the ball applied a force on it and then it goes flying. Okay? So very simple model. Of course, there's 10 pins and the ball might go in different directions and all of this noise. But we just go, we've got two different examples of inertia. The inertia of motion and the inertia of stationariness. The other one that we could talk about is that it could fall, yes, it could fall off. Okay? It could fall into the gutter, at which point, as you know how if you're playing bowling and it's going in the gutter and as it just gets off the lip, all of a sudden if it goes off the lip, then there's no more upwards force and it would literally fall, it would accelerate into the gutter, its motion changes. So in both cases, we could say it was travelling in a straight line until an unbalanced force caused its motion to change. Okay? Could you just add down here, will cause its motion to change. Okay, so an unbalanced force will cause an object's motion to change. If the forces are balanced, then it will keep doing what it's doing. That's a good statement. An object will just keep doing what it's doing if the forces are balanced. Okay? All right. When's recess? 10:40? All right. We'll go till 10:30 and then I've got maybe 10 minutes of videos. So, I just spoke about balanced forces, unbalanced forces. So here's where we now need to look at vector addition again. We looked at vector addition, Aaron. We looked at vector addition with displacement. Now we're going to look at it with forces. Because forces are vectors, they have direction, they can act on an object, multiple forces can act on an object, and we can combine them using our vector techniques. Okay? So, let's consider this free body diagram. A free body diagram is simply a very simple diagram that shows a mass. There it is, it's just a box with an M on it, and then we draw in a couple of forces. Okay? Now, I haven't taught you yet what the Newton is, or the unit. You should know the forces are measured in newtons. We'll learn about the unit of force, next week. Now, what I'd like you to consider is, consider this a tug of war. And the question is, which force wins and by how much? And would someone like to answer that for me? The right force by 20 newtons. Absolutely. I could give that to a 5-year-old, 8-year-old, and they should be able to go, well, that arrow's bigger, it wins, and it wins by 20. Okay? But what I would like you to do is all this mathematics. Remember, you've got to show all your working. This is why I give you a heap of page with lined, sum of all forces. We've looked at that. That capital sigma, that means add them all up. Vector sum, add all the vectors up. We're going to go plus 100 plus negative 80. Why have I called it negative 80? Go Ed.
Let's go the other way.
And so what have I done there? I've assigned a convention. I've assigned the convention that right is positive, left is negative. We get plus 20 as the result. We don't leave it in maths talk. We go 20 newtons right. Okay? So again, gentlemen, I don't want you just writing 20 newtons right. I want you to show all of the working out. Okay? So that is called the sum of all forces. Okay? If I drew these to scale, we could draw a tail to top. Let me try that again. We could draw a tail to top diagram. I probably haven't drawn them to scale though. Whoopsies, try that again. If I add him to him, there we go, top to tail, then my resultant should be pointing 20, if I drew them to scale. Okay? Could I just get now, for now we'll just go, the mass will accelerate in the same direction as the unbalanced force. Hopefully that makes sense. If you apply an unbalanced force, the object is going to move in that direction, or accelerate, I should say. If you kick a football, it's going to accelerate in the direction that your foot applies the force. If I drop something, gravity's acting downwards, and it should accelerate downwards, if that is the unbalanced force. But let's just go back to the first law that says an object at rest will stay at rest if the forces are balanced. Well, if the forces are balanced, we say that the object is in equilibrium. That's probably in more Latin words, meaning equal levels, same. Everything's balanced. Equilibrium basically means that the sum of all forces equals 0. And this is a key statement that year 11s and 12s use in physics. It means that there's no acceleration. So, let's consider this free body diagram. Let's look at 80 newtons up, 80 newtons down. We would say that the sum of all forces equals 0. The object is in equilibrium. So this could be an 8 kilogram, approximately 8 kilogram mass. If I had an 8 kilogram mass, maybe this overhead projector, there's two forces acting on the overhead projector. It's weight. Let's say that its weight down is 80 newtons. Well, if that was the only force, that projector would be accelerating to Earth at 9.8 meters per second, but it's not. There has to be an 80 newton force acting upwards. If it's not accelerating, I can say that all of the forces acting are balanced, the object's in equilibrium, and I could draw it like that if it was a weight force and normal force. Okay? So, the object will not accelerate. I said that if the forces are unbalanced, it accelerates in that direction. If it's in equilibrium, it will not accelerate. Now, I want us to take 2 statements away from this lesson. There's 2 ways that an object can be not accelerating. First off, we could say if v equals 0, then we say, it's stationary. So that's an object at rest. An object at rest will stay at rest. But there's another way that we could be not accelerating, and this is where some students confuse it. You could be cruising along at a constant speed. You could have v equals constant. And that could just be cruising. That's an object in straight line motion, staying in straight line motion. It's not accelerating. It's not changing its velocity. Okay? Two minutes left and then we'll stop the lesson. Let's just consider this plane. Now, there's a very important word that all year 11s and 12s, for them it would be flashing and highlighting and making bells and whistles. It's this word here, constant speed. From that statement, we can interpret a few things. First off, that's a little bit. Acceleration is 0, therefore the sum of all forces is 0. All of the forces acting on that plane must be balanced. Because if they weren't balanced, then the plane would be accelerating. If the plane was accelerating, then it's not going to be cruising at a constant speed. It would be falling or accelerating or going up or slowing down or spiraling out of control, fire and smoke and screaming women and children. But it's not. Everyone's cruising. So let's just quickly draw. Does anyone... Okay, 1 minute left. There are 4 forces that I would like to draw on this. Could you give me one of them that could be acting on this plane right now?
Air resistance.
Air resistance, absolutely. We'll draw a backwards arrow and call it drag. Yep.
Thrust.
Thrust, absolutely. There's a forward force produced by the engines. Sam?
Gravity.
Weight force down. And then the last one, lift, absolutely. As the air rushes over the wings, there's an upwards force generated by the wings. Now, all of those forces must be balanced. If I drew a little free body diagram over here, very, very simple. I've got L, I've got weight, I've got thrust, and I've got drag. We could also, one last thing, we could draw a tail to top diagram. If I drew all of these forces to scale, I should be able to draw them all, and we should get a resultant of 0. That's if I've drawn them all to scale. And I'm just going to cheat a little bit. Okay, there we go. All of those forces. Okay, we're back where we started. Okay. Now, the thrust and the weight could have different magnitudes, but this force and that force must be equal and opposite. This force and that force must be equal and opposite. If any of those were different, then the plane would accelerate in that direction. If the plane wants to go faster, you would increase the throttle of your engines. Your thrust force would get larger than your drag force. The plane would accelerate in that direction. If you want to slow down, you could reduce your thrust. Then the drag would be greater. There would be a backwards unbalanced force, and we would say that it accelerates backwards, meaning it slows down. Okay? We will finish this booklet tomorrow, but for now, let's just look at some videos.